is assignment 3, but I'll tell you more about it after preliminary reading and also tomorrow night. When I go to the lab, I'll talk about how memory can be managed and optimized. I'll walk through the assignment 3. But this is basically the, this is basically the material that I will use for today's lecture. Okay, so the background requirement, I'll walk through what is the parameter extraction routines. Okay, this is actually so essential. Okay, you may have used it since your very young age. Okay, least square fitting of experiments and things. Okay, you may do it graphically, you may do it with a routine. It can be a very long in your applications, all the way, hopefully at the end, we'll see how this actually is the basic component of two of the most popular tools outside where all people are looking for, like principal component analysis and machine learning. Okay, all tied to this particular problem. Okay, so this hopefully this is enough knowledge. Okay, enough unfolding that black box that you understand how least square optimization is done. So when you use running a higher level tool, okay, you understand what is under the hood of these least square optimizations. As I said, it has many applications in most of the statistical analysis, including the PCA and machine learning. Okay, so I use this example to have one stone to kill 3 birds. Okay, apologize for that. Okay, so it's making it a little bit more complicated, but the complicated example being able to debug or validate it in all its method by a simple known example is one of the main spirit in this class. So you are going to build some simple problem for least square fit anyway. Okay, but eventually you are going to build a relatively complex problem. Okay, so I'll tell you what is least square in a minute, but the problem is dealing with the transistor. Okay, so all of you are EE, and probably transistor, it's without any doubt the inventions of the last century. Okay, I don't think there can be any doubt. Okay, for sure, last century we have a lot of important inventions, including radar, laser, all the other things. Okay, but transistor invention for sure dominates the world of computing and communications for the next 100 years to come. Okay, so this is basically a transistor, and I suppose you know transistor, but you may never seen that one of the most popular implementations of the transistor model called EKV model. Okay, which is a sin infinity model. Okay. Continuous everywhere. Okay, and what is a transistor? If you, I cannot even get started it. My life is on transistors, so I don't want to tell you what is a transistor. Okay, but transistor. But one thing, it's highly nonlinear. Okay, if everything is linear, there's no computer, there's no computing, there's no intelligence. Okay, if you have RLC, you can build a gigantic ILC tree. It remains as no computing because every optimization is on the boundary. And I'm done. Okay, so in order to have something that be controlled by the state variables and the Markovian chain that you have seen in the history, you need a transistor. And that also regard is highly nonlinear. Even a switch, a mechanical switch, which you can turn on and off. Okay, on means short circuit, off it's open circuit. Okay, the characteristics is highly nonlinear because between on and off is where nonlinearity is. Okay, so that's this model capture the nonlinearity in your transistor, and is unnecessarily complex. Okay, but for your practice, okay, this is something. It is much more complex than the transistor model you may see in your introductory text, okay? Because you want to do two things. First, you want to be C infinity. C infinity, okay? So it's always continuous. Second, you want to achieve, you can estimate your leakage power. When it's off, nothing is really off. How much it is off is captured at, okay? So that today you do any circuit design, the static power consumption is the number one consideration, okay? So if you are still learning the transistor is off, you can ignore the circuit. You live in the last century, okay? So unfortunately, okay? So know how transistor leak is captured here. From this, this is the first dome, okay? First dome is to give you a highly, first bird. First bird I try to kill, give you a highly nonlinear problem. You try to do optimization, okay? It's meaningful, okay? It's not just that I write a function that's have no meaning, okay? It's a transistor functions, highly nonlinear, and you are going to practice your parameter extraction. The second purpose is that many of these complex systems, in addition to the validation and verification, visualization, not looking at printout, okay? Visualization is a very important debugging tool. Your visual, okay, you see something, okay? Not reading something, okay? You see something, you see a figure. You can capture the essence of information immediately, okay? And this is different from you print out 1,000 columns and you try to go through the columns. You use figures to help you debug, okay? And this is always will become a very important tool, saying that you are later on running principal component analysis. You're going to print out figures and know where is the principal component and know what is important, what is the deviation and things, okay? So learn how to use visualization, not printout, okay? Visualization for debugging, okay, for verification is another important tool, okay, I hope. And this usually, if you think about why you see things, your eyes will directly capture the features, the trend, asymptotic values, all by your eyes, just by looking at the figure, okay. You will be captured many things in a split second, like you learn this pattern. Okay, and this become a important debugging tool. Okay, and this is a simple introductions about how we use the transistor family curve that you may have done for so many times, but why you think that's a transistor family curve, and to this it's a visual debugging. Okay, so I want you to practice on that. Okay, so in addition to the hierarchical testing, okay, many tools use visual debugging, okay, to give you something that you can the user can recognize directly. Even up to today, okay, one of your PCB debugging tool are people to look at it. Okay, you may believe or believe it not, okay, but it is remain true. Okay, any iPhone you have, okay, that PCB board, okay, for sure is running all the testing factors, running all the things. Okay, they are. Let me tell you something that may be discrimination, okay? They hire young women to do that visual debugging, okay? It's find out that somehow women of age from about 17 to 23 have that yet to explain capability of looking at it and capture the detail do pattern recognition. And don't believe it or not, but this is basically the practice in the industry. I'm really sorry to say, but they do use a lot of this young female to do that. And it's statistically very apparent that male does not have that ability, okay? I don't know why, okay? But they have standard tests to figure out who are the good people for doing that testing. And they achieve, when they trained, every person, okay, can look at your PCB layout of iPhone, okay, and determine whether it is good or not, about 5 to 6 boards a minute. Okay, and that's visual debugging. Okay, visual debugging. Okay, just look at the PCB, right? Knowing that what is right, compare, right? Compare. Flash, is this right? Flash, it is right, okay? For sure, there is test vectors validation. Don't get me wrong, test vector validation is very important, okay? But there's also visual, okay? Visual, that's the as good, as advanced as your iPhone, okay? It's meant to be the practice, okay? The layout actually, if you do IC, the layout also have the layout engineer. They train the high school students to do layout verification, okay? For IC layout. Unfortunately, we're still yet to find why those ability exists in those people only in that period of ages, okay? We don't know yet, but it is very well established, okay? Anyway, okay, so that's a visualization. And then you want to train the machine to do it, right? Hopefully to have less dependence on the visual, although remain important, visual validations, okay, that you want to do on this side, okay, on this side. So this is become something we call the expert system. How do you check rules, asymptotic rules, derivation rules, some rules in a complex system, okay? That you think an expert can debug a system better. What is an expert, right? You write the rules down for the experts and implement that in your software, okay? So the visualizations eventually become the expert systems is the second bird I try to kill with this project, okay? So you're already two big birds, okay? I'm sorry, okay? The third bird, okay, is that your project 4 is writing a mini SPICE, okay? If you have used SPICE before, okay, you are going to write a mini SPICE, okay? And I need this, okay? I need the most important component of a transistor. So this will be built into your mini SPICE. SPICE is the circuit analysis. Like PSPICE, yes, you're going to. PSPICE is still something you cannot write as a project because it's too big. You're going to write something smaller than PSPICE.
So are you saying for project 4 actually needs some embedded programming skills?
No.
Because like for PSPICE, you need measuring for voltage, something like need some input.
Yes, I'll give you all that.
So we don't need to like connect this box to the circuit and measuring.
No. Okay. It's a SPICE simulation program. Okay, I'll give you. You are simulating a differential cascaded differential amplifier, but you don't need to know what is that. Okay, it's to you. It can be a nonlinear equations. It's solely nonlinear equation. Fine. Okay, but I want to put in some relevant content, and the relevant content here is SPICE. Okay, and I think it's useful. Okay, if you are an IC designer, okay. So when I interact with the industry today, the circuit design is you can consider as simple or you consider as boring. Okay, so it's captured by one word, SPICE and SPICE to death. Okay, and I'm not kidding about it. Okay, the days of inventing new circuit modules and things has mostly passed. Okay. Most of the circuit are known, okay? So how to get your circuit to do what you want? SPICE and SPICE to death, okay? So an understanding of a SPICE, okay, the internal engine that you rely your life on is good for many electrical engineer. Even you don't do that, okay, treat it as a highly nonlinear problem that I'm training you for optimize, okay? So these are 3 birds I try to kill, okay? First, it's just on the parameter and optimizations. Second, I want to teach you the first step of an expert system and visualization. The third is that this is a component I need for your next projects for SPICE, okay, mini SPICE, okay. So today, I probably run out of spend too much time on this. I believe you have done this over the weekend. Okay, hopefully you have seen the quadratic convergence and quadratic convergence in quasi-Newton, and just crawling convergence in Sakan method. I don't know if you have seen that. Okay, this is the same problem. Okay, same problem from this quasi-Newton. Okay, but I do expect you see quasi-Newton quasi-Newton method to have quadratic convergence. Okay, in the very last line, this is something because the nonlinearity is only in x1. So you start from x0. If you start from the initial guess of 0, you are at God's mercy about which solution you get to. It's just by noise, okay? But if you try any initial guess where this is 2, you will fall into this minimum, okay? You try anything that's minus 2, you'll fall into this minimum, okay? So this is something that you should see if you haven't done it, okay? This is a simple problem that should show you the basic properties of Newton method convergence, okay? And this is purposely engineered here for you to know when there are multiple minimum, you formulate the problem this way, your initial guess will determine which is the basin of attraction you will fall into to find that local minimum. Okay, so please run it. Okay, run it. And then if you use the Sakan method, okay, just using instead of forming the Hessian matrix, okay, which here is not large, it's only 2 by 2, okay. But even if you don't formulate that, you use the Sakan method, a steep descent, you'll find you are gradually approaching that solutions, but it's never quadratic, okay. But all the property remain the same for this problem. Actually, Sakan method, if you do a line search a little bit more carefully, because this is only a quadratic nonlinear, okay. So the convergence is reasonable, okay. Usually if you have fast changing or such slow changing function like exponential or log, then you have more problems, okay. But in here, because the nonlinearity is carried by a quadratic term, it actually is well behaved, okay. Well behaved. You can use the Sakan method to find the solution. Although you should not observe the quadratic convergence. Okay. So let me introduce to you the thing you have done for so many times in your life about parameter extraction, okay? Okay, and as a forward, this is nothing but a nonlinear optimization. It's just a way you write down the objective function. So nothing mathematically new I'm going to tell you. It is nothing but a nonlinear optimization problem. But this is used so often and cast in a way so often, it is worthwhile to look at it separately, okay? But all the mathematical rules and things, formation of the Hessian matrix or Jacobian matrix, the absolute norm, the absolute residual, relative residual is all the same, okay? It's just a way I write down the objective function, okay? So let's look at it, okay? So the real world is many times very complicated, okay? So I describe the real world with, okay, I create a model, okay, to describe this world, right? So these models contain, say, many variables, okay? I denoted, I have n independent variable in this model, okay? Okay? And within this model, I have m parameters, okay? So I give an example for a circuit, okay? An independent variable is something like the nodal voltage, right? You have all the nodal voltage that you can calculate a current, okay? But all the different possible voltages on that network can give you a current. The network, your circuit network, is described by the resistors, the transconductance, all the elements. Those elements are your parameters. Say, how large is that R? How large is the transconductance of your transistor? Okay, those are the parameters, okay? So typically, your model can be written in this way, okay? That your S model is described by the independent variables, okay, n of them, okay, and m of your parameters. Most of the time, n is not equal to m, okay? And most of the time, that this xn will expand to the input vector space. Okay, saying that I have many input, all the different values, you sweep all the values of x1 and x2, while your A remain constant when your network or model is settled. It's just that what are those best numbers in these parameters is something I do not know a priori. I can construct this model knowing that the model changes with x and a, okay, with different dimensions. But I usually do not know beforehand what are those parameters. Okay? So what I do know is I can measure, okay, if I given all these x1, x2, if the independent variable is settled, okay, I can measure the output. Okay? So I create, saying again, back to the circuits, if I give you all the voltage, you can measure the current. Okay? I still don't know what is the parameters in that model that describe this circuit. But if you give me this circuit, right, I can set voltages, okay, to measure a desired variable, say for a current on the branch. Okay, so that's S measure. Yeah.
Right, same thing like measuring. Let's say you want to measure output resistance, so you set a voltage, you measure the current through it.
Yes. Okay. You can. S can be your output resistance. Fine. So you know, you write in a way of, but you change all the voltages or current, so you measure that output resistance, and you have a model for the output resistance containing not only the nodal voltages but also the parameters. And the parameters are those that I don't know yet. Okay, saying that you have something like this. Okay. Okay, so if I give you this and this, right? These are the x1 and x2. Then I can tell you, I can measure V out, right? I can measure this, right? But I don't R and the GM RO of these transistors are the parameters that describe this circuit. This is the measurable. This is your S. This is your x1 and x2, right? The R and GM and RO for this circuit is the parameters. And I don't know those parameters usually. Okay? I need to extract from the measurement knowledge to know what these values are. Okay? So you probably have used this a lot of time, but just that now I cast to a formal mathematical problem. Okay? And what is this for? Okay, so this it has a lot of a huge application. Okay, so notice for every legitimate input factors, like you can sweep this, right, and you can generate thousands, millions of these output, right, and you can all measure it. Okay, but the parameter remain as fixed. Okay, the dimension of the parameter remain as fixed. But I can use the sweeping of the independent variable to generate millions of the things I can measure, all the data, right?
Oh, and then you can solve for the parameters.
Yes, well, the whole point is to solve for the parameters, right? So this is the way we understand people as well. You have done this all the time, right? So you have these, yes?
So when we do this kind of question, are we consider this kind of transistor in the steady stage?
No, don't have to.
But
for sure, the example I give you, this is steady state analysis.
Yeah, but since like
for sure, this can be a function of t, right?
Yeah, but
this can be a function of t.
Most it can be like not saturation or some kind of like forward stage.
Sure, totally possible. The transient step is actually the one you will implement in your mini spice. Just that hold your horses for another 2 or 3 weeks. Okay, I'll show you the entire span when your independent variable become time dependent. Okay, so let's just think x1 and x2 are independent variables. Okay, let's just pretend that. Okay, for sure, in the real world, we only live in the 4-dimensional world. There's only x, y, z, t as the true independent variables. Okay, but this is a simpler view. Okay, I'm treating x1, x2 as true independent variables. Okay, I'm only looking at from that view. I'll teach you a view how to look at from a differential equations that all your state variables is no longer an independent variable. It's a function of the independent variable of time. That will come later, okay? But now just treat them as independent variables, okay? They can change whatever they are, okay? So in this, you see that you can test a lot of this, right? So S can also be a factor of rank L, okay? Your independent variables here is rank N. Your parameter space is rank M. And your S can be a factor of a rank L. You have multiple things that's measurable, with L. And we can use the norm of S to do the things that follow on, okay? So just that. But I will not make that complication now, okay? But that step is easy, okay? If you have multiple things that's measurable, okay, and you want to fit the same model, okay, then you are going to write down the norm of that S factors of rank L for the optimization, okay? But that I will restrict later, okay? But it for sure can be generalized easily to multiple measurable things, okay? Okay. So now, least square model parameters can be simply read down by this, right? My objective function is for every instance of your independent variables, okay, you have a S model, you have a S measure. Remember, this S model is not something I know yet because I haven't determined the value of A or the parameters. So I don't know that yet. So this is a symbolic objective function. Okay, S measure I have. Okay, I have input all the S measure corresponding to what is the independent variable of X. So this is known already. But S model remains symbolic at this stage because I cannot compute it yet because I don't know the value of all the parameters. I can guess. Okay, but that remains as an initial guess. Okay, I can guess, but this is not settled yet. Okay, so I know that the model will describe this measure by minimization of this V, right? S model minus S measure square, and I sum up with all the I, and that I can go from 1 to a million, even though I'm only looking for 2 parameters. Is that this summation can be huge, but the parameter dimension space may be small. Okay, let's try to see. Okay, so in order, if this is, I cast this as the objective function, then the optimal value for the parameters can be simply written down by this, right? Your gradient with respect to the parameter should go to 0, and the Hessian matrix with respect to this should be positive definite to give you a minimum. That is what you learn in the nonlinear equation, nonlinear optimization, right? If this is my objective function, describe the difference, right, for S model and S measure, and I take the second norm. If this is my objective functions, then I know the parameters that describe the S model will best fit my measurement data when these things happen, right? When this gradient goes to 0 and the Hessian is positive definite. Right? Okay, let's think about it, okay? So, since V is always positive, okay, V is defined by this. V is always positive, okay, so it's simple to prove the Hessian matrix is always positive definite. Okay, you have a minimization problem. Always. Even your model is very bad. The question I'm asking is not how bad is the model. The question I ask is, what is the minimal error the model describes the measurement? So there's always a solution. It can be a bad solution, but there's always a solution. Right? The question I'm asking is not whether the model is true. The question I ask is, how good is that fit? The fit can be horrible. That can be the answer. But after you optimize it, you get the S model with all its parameters. And this V remain huge. Even it's a local minimum, but it remains huge. That means your model is very poor. Big deal, but you still have a solution. Okay, always have a solution, okay? The form of the sum of the square for minimization problem always has a solution, okay? It can have multiple solutions, but it can always have at least one solution, okay? So this is described here, okay? We'll always have exact m equations, right? Because I'm taking the gradient to be 0. So the number of equation going to 0 is identical to the number of parameters. That's where I take my partial derivative, right? So it's always the exact number, okay? Exact m equations for the m parameters, okay? And this is not underdetermined, it's not overdetermined, okay? It may have multiple solutions, but it always have at least one solutions, okay? That describe a local minimum of that fit, okay? Of that fit, okay? And you can see V is nonlinear, even so S can be linear, okay? But there is a caveat to this. I'll show you with an example, okay? But this V is generally nonlinear because of the square, okay? But there's a caveat to this. I'll show you in the linear fitting, okay? That the equation actually, this equation is linear, okay? The gradient equation is linear, okay? So that's the exception, okay? There's only one exception, okay? So only in your linear regression, your gradient is linear, okay? Your objective function remain quadratic, okay? But your gradient become linear, so you can solve linear regression in one step, okay? But I'll come with the example, okay? Okay. So the purpose of this, okay? Let me just show you why this is so important, okay? So you can measure many S in this, okay? Once I construct the model, I can make an estimate about something I cannot measure, okay? For example, the S is the power grid network, okay? And I'm asking, in what kind of usage the network will be unstable, okay? Theoretically, you can measure that, but nobody will allow you to measure that, right? Because you are destroying the grid, right? So what do? You make a model, you do everything you can for measurements, build a model and let the model to go to instability, right? Totally safe and totally real, okay? You just don't experiment on that, okay? At least not experiment that often, okay? Too expensive, way too expensive, right? And there are many problems. You're asking when will it become failure or something. Many times that you cannot do that measurements. Although you can do many measurements, but you cannot do measurements on the instability or things that has to come from model, okay? And how your model parameters is accurate will determine how good you can estimate the instability. It's very important, right? Okay. So, and other problem like this model can be, I can measure a polling, right? Like a social science. I want to know the ideas of the next election. I can do a polling, okay? And I build a model, right? How these people's response will be. I build a model, and I use the polling to calculate the parameter in my model so I can predict who will be elected as president. Future things for sure, it's a prediction. Okay, you cannot, that means that you cannot measure it at the present time. But you use the present polling data, calibrate the model, right, to get the predictions, okay? And the model can be saying that you can do a regressional test, right? Because even I don't know that time, but now I know, right? Because now I can, now I have a lot of knowledge of the previous election, right? Where I know all the polling and I know Trump is finally elected. I can run that to see if my model is correct, okay? I also know how Clinton was elected or before Obama is elected, right? And all the polling is also done at that, right? So if your model will become more and more accurate by this learning, right? It is, you can learn from the past and fit it and then learn it and this become part of the machine learning, okay? Perfection of your model, right? By including the more representative variables and parameters so that your model become good. Okay, you can run regressional tests, right? So in regressional tests, building evolve your model together with what is known. That's just learning, okay? Whether it's machine learn that, or you learn that, or whoever learned that, is learning. Okay? Use your past knowledge to calibrate what is in your model, okay? And that is nothing but a parameter optimization problem. How you write down that S, okay, is still of great knowledge, but mathematically it's simple. Okay? How the physicist or the social scientist can be write down your best model. That's different, okay? That's for sure. Take years of perfections. And our dream is that the machine or the computer can gradually even know how to write this model. Then I can get rid of the human, okay? But if not, okay, then at least if S model is given by a person, okay, and these become a mathematical problem. Simple, okay? It's just least square. I'm doing an optimization, okay? Okay, so this, okay? So S may not be smooth, okay? Which makes the numerical derivative, okay, noisy, okay? So usually we would like the S model can be made sin infinity, meaning it can take all derivative with respect to either X or A and remain continuous, okay? Your measurements, unfortunately, will contain noise and uncertainties. That's just a matter of life, okay? A noise and uncertainty in the things that you measure is one thing, maybe small. You take a derivative, you are totally dead, right? If anything that's noisy and you don't do anything about it, you just take a derivative of 2 points. 2 points contain noise, then there's nothing you can say about that derivative, okay? But the model is different, right? I can make it C infinite, okay? Once I fit my model parameters, I take the derivative in the model, not from the measurements. Why? Because measurement has noise. And differentiation of noise is death. It's a delta function, right? So you cannot, okay? So that many times that we make measurements S so that, okay, it can take the derivative, okay? Many times I want to know the derivative, right? And I cannot get that from measurements. I have to get from model because measurement has noise. Okay, so least square fitting for a linear line. So I decide to lay it out, okay? So for you to understand what is going on, okay? So let's work out the simplest example, okay? This example actually is meaningful because it's the variation of it is a power law. You will see what is contained here, okay? So that let's have two independent variables, X and Y. I have two parameters, okay? I have two parameters, A and B. Okay, so in this very simple line, y equal to ax plus b, that you know since the grade 7, okay, contain two independent variables and two parameters, okay? Okay, and now say I have 4 points, okay, just for I choose 4 because of the size of my screen, okay, for sure. This is, once you follow the derivation, you can generalize to a million point, okay? And this is the linear regressions you have seen, right? So you have this scatter plot in the XY plot. You're asking what is the straight line that described by y equal to ax plus b that best fit this, right? For sure, there's all these errors, okay? But you are minimizing the errors. You have done this a million times since grade 7, right? Linear regression, okay? So now, according to the procedure I do, v as a function of a and b, I'm going to take the gradient and Hessian is VAB equals to this least square, right? Very simple. Remember here, look at it, okay? The A x0 plus b minus y0. This is my first instance of measurement, right? I know x0, I know y0. I don't know a and b yet. Okay, so these become equations of a and b, right? With the 4 known points of x0, y0, x1, y1 things, okay? Even with the 4 points or whatever points in here, you can always ask the question, what is the closest line? Even though the fitting is poor. And that line always exists. Okay. Right. So you can write down this V, walk through, okay, take the partial with A, become this equation. Take the partial with B, become these equations, reorganized according to A and B. Okay, your F1 coming from here is this. Your F2 is this. Okay, so it become a for this only this case, the gradient of your least square is linear. Okay, so this is actually is A has a coefficient, which is the sum of all the x squares of the known case. B is the sum without the square, and the right hand side is this, right? The product. Okay, F2 is this is the sum of all the known coordinates. B, this is always 4. It'd be weird, but that's true. Okay, we can just these steps are just so easy. Okay, so it will be just then this is right hand side. Okay, so you can solve this in one step, right? I want know that this is in one solution, right? With all the known points, I get the A and B. Okay. Yes.
Okay, what's F1 and F2 again?
F2 is coming from the take derivative with B.
Oh, okay.
Nothing. This is from here to here is only reorganized to illustrate the point. Okay, that's the. But I didn't do anything. Okay, you can stop at so I want to make this 0 and this 0. Fine. This is F1. This is F2. Yeah, okay. So I didn't touch anything else. Okay, but for sure after this reorganization you will know if I have 1,000,000 points. You know how to extend this, right? So that's 1,000,000 points, fine. Also here it's only 4 points, so 4 terms, okay? But it's 1,000,000 points, you just keep on adding the things will be that solution.
But since this is linear, it doesn't even matter if you had 4 points or 1,000,000.
It has to be more than 2 points.
Yeah.
Okay.
But anything more than 2 should solve it because it's linear.
Yeah, it's linear. Yeah, for sure. My model is linear, right?
Yeah.
So it is my it can be totally scattered. Yeah. It can be even scattered like this. But there is still a unique line that is the least square of the point given. Okay. So there's still a unique solution. Okay. If you look at this, take a step and look at it. Okay. The formulation and all these things. There's always a unique line that minimizes this V in your linear regression.
But is there any restriction on how our original function should be? What if like it's super nonlinear? Then
Oh, sure, yeah, sure. Then it will not be this simple. So this V, your model can not be this, okay? If your model is this, okay? Say, let's just do that. Your model is ax cubed plus bex plus x squared plus b, but c plus d, okay? This is your model, okay? And then you can do exactly the same step, right? The known points, right? Formulate the v, take the partial derivative, and solve when these go to 0.
And how would we know like till which power should we go? Ax cubed, ax4?
That's the model. Okay, that's something is the genius or the physicist's job. What is the model that describe your measured data? Okay, that's undetermined. Right? That's for sure. A transistor, right? You come up with this EKV model, the EKV model, or the square root model, or in your social science, you come up with item response models. Okay. The models, okay, that describe, you think that model describes the essence. And it can contain any arbitrary parameters, okay? And once you make the measurements, I can tell you what is the parameter that best describe your measurements, right? And there's always one solution, right? See, okay, and here, linear regression even can guarantee there's one and only one solution. Linear regression, like this, these can have multiple solutions, right? Because these equations are nonlinear, so I know there's a solution, but it can be more than one solution. Okay, in linear regression, there's only one solution. Okay, you can see right there, and you have used linear regression for all your life, right? Long time. Just this is the essence. Okay, I think maybe if this is the first time you see expanded out, okay, congratulations, you see expanded out, okay, it's nothing. If you have seen this, okay, boring, okay, this is nothing. But this is how you get the linear regression. It's guaranteed as a solution. Okay. So you can try it out. Okay, so this is the Hessian. Okay, you can do solving this This is the right hand side. You can solve your Hessian times that A and B, and equal to the right hand side. You get your A and B exactly. Okay. You can. No time to try it out. Okay, so these are the purposely made noisy. This is fit to y equal to 2x plus 1. Okay, you can try it out. Okay, so you may not retrieve that exactly a equal to 2 and b equal to 1, but it is an optimization problem. Will give you a unique solution. Okay, try it out. Okay, here I give 6 points. Boy, but that's big deal. Okay, just change it to 6 points.
Wait, you didn't give us the model. We're not supposed to.
No. I generate this data from injecting noise to y equal to 2x plus 1.
So are we supposed to know that?
You don't. You usually don't. You don't. You know this is y equal to ax plus b, right?
Oh, we know y is equal to ax plus b.
I want to know what is a and b.
Yeah, so we know that equation.
You know that this equation, but you don't know the value of a and b, right? So this is the procedure will tell you how to solve for these a and b, as in linear regression. Okay. Okay, so I tell you how I generate the data. I generate the data from these equations, and I inject noise, like emulate the reality. That's it. You should get a and b close to 2 and 1. Okay. It will not be exactly 2 and 1. Okay, but that's how I generate my data. I write a random noise, right? Add it to the numbers. Okay. Simple, okay? But this is too simple, okay? The next one is meaningful. Let me finish that, okay? Okay, this is 5 minutes faster, okay? The other very popular fitting is the power law, right? You should have done this many times as well, okay? So there is a data you measure, you do the power law fitting, okay? What is power law? Power law is y is equal to axm. Okay, now you have independent variables of x and y, and now your parameter is a and m. Okay, before it's a and b in the linear regression. Okay, I use power law as a example. Okay, and also as illustrations of the game of least square fitting. Okay, because power law, if you take a step back, is nothing but linear regression, right? By taking the log x and log y. Power law is linear regression. There's really no difference. Right? You take the log on both sides of the equations, right? You get the power law as a equal to ax plus b. Power law is more constrained because that you take log, nothing can be negative. Okay, that's the only constraint. Okay. But it is the same problem. Okay, but let's work at this problem. Okay, so because asymptotically I know it's equal to y equal to ax plus b, but you will actually get a different set of answers. Okay, and let's see what the answer we get. Okay, so the v should now be this function, right? This is my model ax0 m minus y0. But the first point I know, square. Second point I know, third point, fourth point, right? I take the derivative with respect to a and m and make them go to 0, reorganize them, I get this. No trick, okay? This is nothing but algebra, right? I write down the objective functions as a least square principle, and this now remember this is highly nonlinear, okay? But so I get, okay, but I can take the derivative go to 0, I can reorganize them to here. You can see that a here for the first equation remain linear. Okay, a here is quadratic, okay, here. But m is remain highly nonlinear, right? Highly is an exponential function. Right? So if you write down your Hessian, This is your Hessian. Okay, this is actually, this one is too long. I won't. This is a closed form, but I just didn't write it down. Okay, just that you can solve this nonlinear optimization. Okay, the data set I give here, try it out. Okay, is just taking the exponential of the previous table. So supposedly you should get the exactly the same fitting. These are the same data set. Okay, one I look at is a linear regression. The other I look at as a power law. Okay, but there are to the digit exact data point. It's just that one I have take log. Okay, and you will find that all of a sudden the endpoints become much more important. Okay, these points, because of the large values, they all of a sudden become very important. Okay, these minute point in AS equal to B, the beginning point and the end points are of equal importance because they are combined together in that. In these equations, you will find that when this is dominated by the large terms, okay, just the way it is. You see, when you look at something with an exponential lens, then the minute difference in the large number become important. If you look at it from the log lens, the minute difference in the small numbers become important. If you look at linear, then everywhere is the same. Okay, so do try it out. Okay, so this will teach you. If I think you have done linear regression, but try out this formulation. Convince yourself this is the parameter optimizations, and these are the way different view of the objective function. Okay, so you get a feeling about what you're dealing with in the least square. Okay. Sorry, I don't have enough time for you to do this in the lecture. I will try to reserve more time in the future that you can have practice during the lecture. Okay. I have